Hey, welcome back to Charlie in Tech. Make sure to subscribe and like my videos so that you can come back to this channel. This is the second part of exploring large language models with me. In the first part, we already discussed how language processing is done. We understood the core concepts and reached next token prediction. Now we should understand also how we make LLM, our model, behave the way that we want it to behave. So how do we ensure that actually model does what it has to do? How to ensure it gives you better answers? And how we can use them in different scenarios, we will see in this second part. Also, let me tell you that there can be different usages of LLMs in different fields. Some fields are more statistical, like scientific, which means that our LLMs are expected to give this or that answer. Some fields are more of a predictory fields, and we should ensure that it predicts the right solutions and gives the best answers. So let's start from the sampling and temperature and go on. We already saw what is next token prediction. Let's continue about sampling and temperature. At the part first, we already learned that an LLM calculates probabilities for possible next tokens. If I write like the cat sat on the, if you remember that example, the model may consider mat the most likely continuation, but floor, chair, sofa could also be possible, yes? So how does it choose? This is where sampling comes in. And one important parameter is temperature. At a low temperature, the model behaves more conservatively and favors the most probable choices. Think of going to your favorite restaurant, for example, and ordering your usual. At a higher temperature, you're basically saying, surprise me, please. Less probable choices get more of a chance, which can make the output more creative and less predictable. For extracting information from an invoice, we probably want consistency. For medical reports, we want consistency. For brainstorming product names, marketing ideas, some randomness can be useful. You may also hear about top K and top P or nucleus sampling, yes? These are other ways of controlling which possible tokens the model can choose from. The main idea is simple. The LLM produces probabilities, and the decoding strategy determines how we select from them. Before we talk about fine-tuning, let's quickly connect these three types of machine learning you may already have heard about. This is very important to differentiate. Supervised learning, for example, we give the model labeled examples. Think of emails already labeled as spam, yes, in your mailbox, or not spam. And the model learns from those examples. In unsupervised learning, we don't provide any labels or examples. We give the algorithm the data and let it discover patterns or groups itself. For example, it might discover different types of customers based on their behavior without us defining those groups beforehand. And in reinforcement learning, which is my favorite, a system learns from feedbacks or rewards. Think of learning a game, yes? Actions that lead to better outcomes receive higher rewards. So the system gradually learns better behavior. For LLMs, large language models, there is another important term. The text itself provides the training signal. For example, the model can try to predict the next token and compare its prediction with the token that actually appears in the training next. Now we can understand fine-tuning more clearly. Let's go on with fine-tuning. We already have a powerful pre-trained model, yes, but maybe we want it to become better at a particular task or behave in a particular way we want. Instead of training another LLM from zero, we can fine-tune the existing model. For example, let's think of a doctor who first learns general medicine and later specializes in cardiology. They don't start their education again. They specialize on top of what they already know. Same happens here. One common approach is supervised fine-tuning or SFT. We provide examples of inputs together with the outputs we want. For customer support, that could mean customer questions paired with high quality responses. We may also hear about LoRa or low rank adoption. You may have heard about this if you're into AI. It's a parameter efficient fine tuning technique that actually allows us to adapt a model without updating every parameter in the entire model. So broadly speaking, pre-training gives us general capabilities while fine-tuning helps us specialize or adapt them. Let's go on with RLHF, which is third type of learning we just mentioned, yes, becomes especially relevant here, reinforcement learning. How do we decide what makes one answer better than another? Imagine asking an AI to explain quantum computing to a 10-year-old. Two answers could be technically correct, but one of them might be much easier for a child to understand. RLHF stands for reinforcement learning from human feedback. In the classic approach, humans compare different model responses and indicate which ones are more helpful, clear, safe. Those preferences can be used to train a reward model, and the LLM can then be optimized towards responses that receive better scores. You may hear technical names such as PPO or proximal policy optimization and neural preference optimization, approaches such as DPO, direct preference optimization. You don't need to memorize them now. The important idea is that human feedback can help shape how a model behaves itself. But remember, an answer that humans prefer isn't automatically factually correct, not in all situations. This part, context window memory, is my favorite one. Let's talk about them because people often treat them as the same thing, but they're not. The context window is the amount of information the LLM can work with during a particular interaction. That can include your prompt, previous conversation messages, system instructions, retrieved documents, and tool results. Think of it as your working desk. You may have an entire library available, but only a certain amount of information can be open on your desk at one time. Memory is different. An LLM doesn't automatically remember every previous interaction forever. Applications can build memory around it by storing information externally and retrieving it when needed. RAG or retrieval augmented generation is a good example for this. If a company has thousands of documents, we don't give all of them to the LLM with every question. The system retrieves the most relevant information and adds it to the current context. So when AI seems to remember something or know private company information, there may actually be databases and retrieval systems working around LLM. Now we get to one of the biggest limitations of LLMs, large language models, hallucinations. They always happen no matter how good model is built. A hallucination happens when a model produces information that sounds convincing but is actually wrong and invented out of nowhere. Why? Remember that we've been discussing from the beginning an LLM is predicting plausible next tokens. It isn't automatically checking every sentence against a verified source before answering. Imagine I ask you for the exact title of an obscure research paper you've never seen. You would probably say, I don't know. But if you are forced to produce an answer anyway, you might come up with something that sounds believable. LLM can do something similar. Sorry, it sounds like a pathological liar, and there are also people like that, but yeah. LLM might invent a paper, quotation, statistic, or even a source. We can reduce hallucinations using RAG, trusted databases, search, external tools, citations, validation, and human review. Combining all of them is the best approach, by the way, as much as you can. But a confident answer should never automatically be treated as correct answer. That's why whenever you see AI model, there is always a caution message written that this is AI, it's never perfect, etc., etc. What actually happens after you type a prompt and press enter? This process is called inference. Your prompt is tokenized. We already talked about tokens. But let's go on with the same token topic. Those tokens become numerical representations and they are processed through the transformer layers. Self-attention helps the model understand relationships across the context. I've explained these things also in the first part, so if you haven't watched it, go on and watch it as well. It is in the same playlist. At the output, the model produces raw scores called logits for possible next tokens. Those scores become probabilities, and decoding strategies such as temperature or top P helps us select the next token. That token gets added to the sequence and the process repeats. That's why you see the response appearing token by token. Real production systems use optimizations such as caching, batching, quantization, and GPU acceleration to make this faster and cheaper. But conceptually, remember, prompt goes in. The model calculates probabilities, one token comes out of it, and the process repeats. So, where do we actually use LLMs? Chatbots are the obvious examples, but LLMs are also used for coding assistance, document summarization, translation, information extraction, customer support, analyzing feedback, searching large knowledge bases, HR portals. Increasingly, we also connect LLM to tools. Imagine asking an AI travel assistant, find me a flight to Paris next Friday under 300 euros. The LLM itself doesn't know today's available flight. Instead, it can understand your request, call Flight API, receive current results, and explain these results to you. That's why a real AI product is usually much more than an LLM. We may combine the LLM with RAG, vector databases, APIs, traditional databases, business logic, guardrails, monitoring, and user interface. The LLM may be at the center, but there is often an entire system around it. And that's also why we need to understand the limitations that we have. We have already talked about hallucinations. Models can also reflect biases from their training data. I may have another short or may not, I don't know, about biases to explain them better. And large models can require significant computational resources and money. For real products, latency and cost matter. If millions of users are sending requests, even small differences, response time, yes, or token usage can become important. Security matters too. AI applications can face problems such as prompt injection, sensitive data exposure, or inappropriate tool access. Even if a model has a huge context window giving it more information, doesn't automatically mean it will reason perfectly over anything. These systems are extremely powerful, but they're not magic. Building reliable AI means understanding their limitations as well as their capabilities. Also, it's very important in product management if you're dealing with AI products. Of course, you have to understand the system. Let's connect everything we have learned in this with these LLM topics. Text becomes tokens. Tokens become numerical representations through embeddings. I brought examples of address and home address, if you remember these parts. Transformers and self-attention process those representations, and during pre-training, the model learns through self-supervised learning to predict tokens. Then sampling influences which token is selected. Supervised fine-tuning can specialize the model, while RLHF and other preference learning methods can help shape its behavior. Context windows determine how much information the model can work with at once, while external memory and RAG can provide additional information when needed. And during inference, all of this comes together to generate a response one token at a time. Once you understand this whole pipeline, LLMs become much less mysterious. They are still incredibly sophisticated, I know, but now you can see the main pieces behind what looks like a simple chat window. We finished this series, these two parts of what is large language model. Whatever part is more difficult, we will explore further. We deep dived into large language models, and I intentionally kept a real technical terminology, because if you want to understand AI, you should know concepts like supervised and self-supervised learning, tokens, embeddings, transformer, self-attentions, RLHF, inference, context windows, fine-tuning, RAG, and hallucinations, all of it. The point of AI in plain English isn't to remove the technical side completely, it's to make the technical side understandable to majority of people. From here, we will start taking these concepts one by one and going deeper into tokens, context windows, embeddings, vector databases, retrieval augmented generation, memory, agents, MCP, prompt engineering, fine tuning, and eventually how real AI products are actually built. And in the end, I also cover the technical product thinking behind building the best AI models with your team. I am super good Charlie in tech. Thank you for watching. And yeah, I will give a little speech before the next episode. Thank you. Congrats! You learned a lot of things about large language models in these two parts. Make sure to learn new things and stay in this channel. Make sure to subscribe, and make sure if you liked the video, if you really liked it, please also share it with your friends and share in your social media platforms. Okay, and if you have any questions, you can ask in the comments, by the way. And in the next episode, we are going deeper into something very interesting. RAG, Retrieval Augmented Generation. We will see how embeddings, vector databases, and retrieval work together to give an LLM access to relevant external knowledge instead of relying only on what it has learned during its pre-training and training. So next up, what is RAG, and embeddings and vector databases are explained in more details than in previous videos. I'll see you there. Bye bye.